The second part of our course is a systematic framework for cluster analysis in networks, introducing the order in the jungle, as we said. There are two parts here that I wanted to cover. Of course, the big one will be this clique relaxations taxonomy, the framework. That's the main topic of discussion today. And then the plan is to gradually move towards the next day. Tomorrow, the plan is to discuss the exact algorithms for finding the maximum size or maximum weight structures of a given type in networks. And in order to do that, we need to understand the complexity. So I was planning to kind of go over this quick crash course on complexity theory for those of you who have never seen really complexity theory. Like, you know, if you're in computer science, of course, you have to know this stuff, right? So from the courses that you take, but we have a diverse audience here. So, and I assume that most of you were not really introduced to the theory of complexity, like NP hardness and NP complete problems, right? I wanted to just briefly touch upon the subject to kind of give you an idea of what it is about. With this clique relaxation taxonomy, the whole idea is based on what we call the elementary clique defining properties. So this is something that we will introduce first. Essentially, we'll observe that because clique is essentially perfect, right? You could define the clique equivalently through many different graph theoretic invariants. Many of these structures that you have in networks, sometimes even remote from clusters, can be used to equivalently and uniquely define cliques, and this is what we'll call the elementary clique defining properties. And then we'll discuss the nature of clique relaxations. We'll use these elementary clique defining properties to essentially reproduce the definitions that we have seen in the jungle slide. We'll do it in a couple of different ways, and we'll discuss the nature of these different types of relaxations in the next part here. Then we'll talk about what we call the higher order clique relaxations. Higher order would be something similar to this lambda gamma quasi-clique, when you're considering a couple of different elementary clique defining properties combined to define the clique relaxations. And then the last topic here will be trying to understand the cohesiveness of what we call canonical clique relaxation. So all of this will be discussed in more detail later today. This is again that messy slide with a lot of definitions, right? You see that there are many of them, and these by far are not all the definitions that are available out there. So, but I think this is good enough already to have a little bit of information overload. The discussion that we'll have next is actually based on this paper that we co-authored with two of my former PhD students. This is where we build this framework, which can be used as a source of many ideas, actually, of studying these clique relaxations in a systematic fashion. The idea of these elementary clique defining properties goes as follows. Clique, the way we defined it is what? First, we said it's a subset of vertices that induces a complete graph. Then I think formally the way we stated the definition was, we said it's a subset of pairwise adjacent vertices, right? How about trying to look at different graph theoretic concepts characterizing the vertices or edges or graph structure, and try to see if I can have an equivalent definition of a clique using that concept, like distance, for example, right? I can say that a subset of vertices is a clique if and only if the distance between any pair of vertices is 1. Right? So vertices are distance 1 away from each other. So here 1 is the key word. Diameter, same thing, right? So a subset of vertices is a clique if and only if the diameter of the induced subgraph is 1. The next characterization is somewhat totally different. Here, let's take a concept like domination. Okay, so a set of vertices is called a dominating set if every vertex from your set, the big set of vertices, either belongs to the subset D or has a neighbor in D. Imagine you have some subset of vertices D here, So there are a bunch of vertices, and then there are many more vertices outside. If I look at the vertex from outside in the dominating set, I must have at least one neighbor inside, right? So you could have more than one neighbor, but you know, every vertex from outside must have at least one neighbor inside. So this is what we mean by a dominating set, right? Now, how about using this concept of dominating set to equivalently define clique? So it seems like very different from clique, right? Nevertheless, you could say, you could observe actually. So look, here you have a clique. So in a clique, how many vertices do you need to dominate the whole set? Just one, right? So any vertex is a dominating set. So because look, I pick any vertex, that vertex is in the set. Every other vertex from outside has that vertex as a neighbor, so it's a dominating set, right? Now, if you think about it, is this an equivalent characterization? Can you have another structure where every vertex is a dominating set? It's a unique characterization of a clique, right? So there is no other structure like this. So let's say imagine if I had this edge missing here, right? So if it was missing, then neither vertex 3 nor vertex 2 forms a dominating set anymore. If every vertex is a dominating set, this must be clique. So this is if and only if relation, right? So in terms of domination, we can also provide a clique definition. When you introduce the definitions, I could start with dominating set and then say, okay, a clique is a subset of vertices such that every single vertex forms a dominating set. And this is a legit definition of a clique, right? Probably not the most straightforward and not explaining the concept the best, but in math textbooks this is common, right? You can have some definitions that look very confusing and take a while to figure out what it is. One thing that I wanted to point out before we move on is that, look, I put in bold 1 in each of these definitions. So you have 1, 1, 1 here. Now, if we are looking at degree, then we can say that a subset of vertices is a clique if and only if each vertex neighbors all other vertices in the group, right? So here we have not one, but all. Kind of the opposite, right? So then the edges or the density, the induced subgraph has all fraction 1 of possible edges, right? So again, all. Connectivity. All but one vertices need to be removed to obtain a disconnected or trivial induced subgraph. So these are all equivalent definitions of a clique, right? So clique is a unique structure for which this works as a definition. This proposition essentially summarizes all the equivalent definitions of a clique we discussed in the previous couple of slides. So a set of vertices is a clique in G if and only if one of the following conditions hold. Any of this is an equivalent definition of a clique. The distance between any pair of vertices in the original graph is equal to 1. If you are talking about induced subgraph here, then it becomes a diameter. So then domination-based definition, the single vertex is a dominating set for any vertex. Then minimum degree, delta small of G of C has to be equal to cardinality of C minus 1. So the number of edges has to be equal to cardinality of C choose 2. So then edge density is equal to 1, and then the vertex connectivity is equal to the cardinality of C minus 1. All of these are elementary clique defining properties, as we call them. And now, how do we use these elementary clique defining properties to get the clique relaxations? There are two ways according to which we can meddle with these definitions a little bit. Essentially, what we observe in these relaxed cliques is a certain violation of the properties that we have in the clique, right? But in a controlled fashion. So it's like you introduce the error in the system, but you kind of control it. A controlled error. And this is the way we can define the clique relaxations based on this elementary clique defining property. So this is restricting a violation of an elementary clique defining property. So essentially, if you look at all these definitions, you can replace one with at most S in these elementary clique defining properties, or replace all with all but S. And you'll see that this will cover a lot of the concepts that we discussed so far. You introduce an error, a negative thing in the system, right, but you're controlling it. The other approach is more of the positive thinking. So you look at the property of a clique and you just force this property in a clean form, state that property for a fixed cardinality clique, and then just use it as a definition for an arbitrary size of a graph. This is what we call ensuring the presence of elementary clique defining property stated for a fixed cardinality clique. So you just use an elementary clique defining property stated for a clique of cardinality k as the definition of your clique relaxation, just like we did with k core. So now, look, these are just a couple of very simple rules, right? So essentially, the system is as follows. So you just think of any graph theoretic concept really, and see if you can come up with the definition of a clique through that particular concept, right? And then apply this or that rule, or try both, and see what you get for the resulting clique relaxation if it is something meaningful, right? So let's go over some of this now for the different elementary clique defining properties and see what we're going to get. So first, for the distance and diameter, so we obtain, of course, S clique and S club, right? So we apply first restricting the violation way of defining the property. If I apply it for distance, pairs of distances at most S away from each other is S clique. For diameter, I obtain S club, right? These illustrations here just provide the corresponding protein complexes that have the structure that essentially can be described using this clique relaxation. If you look at the domination, so yeah, this is the third definition, elementary clique defining property that we listed, right? Any vertex set of cardinality S instead of 1, so you replace 1 with S, ensures domination. So essentially every set of S vertices in your network is supposed to be a dominating set. Then we can actually easily show that this essentially is the definition of an S-plex. So remember, the way we defined the S-plex was the degree of every vertex is at least cardinality minus S. You could equivalently define it as a set of vertices such that every subset of S vertices forms a dominating set. By applying this logic of restricting a violation to the elementary clique defining property based on domination, you obtain S-plex. So now, restricting a violation with all but S rule. When you use these definitions where all pops up, like each vertex neighbors all but S vertices now, again we obtain the definition of S-plex. See, different elementary clique defining properties, when relaxed according to this first rule, they result in the same clique relaxation, which is S-plex, so which kind of gives extra points to S-plex, I would say, because it comes from different sources, right? Underlines its importance. Then vertices induced a subgraph that has all but S possible edges. In the definition of a clique, it was all edges. We replace it with all but S. We obtain S defective clique, right? So then all but S vertices, so if you apply it to the definition based on connectivity, right? We saw that you need to remove all but one vertices in order to obtain a disconnected or trivial subgraph, right? Now I replace all but one with all but S. Then we obtain a concept that we call S-bundle, so I put it in the frame here because this is something that was introduced in this paper essentially. Nobody really considered this before in the literature. But you know, if you look at this structure, so what is S-bundle? So this is a very, very robust cluster. Which is actually, as a cohesive subgroup, it's a lot more meaningful than this K block that was considered in the literature. And then the argument here is that, look, the only reason this type of structure was overlooked as a definition of a cohesive subgroup was because of a lack of this simple but very systematic framework of looking at things, right? So this S-bundle structure, since we introduced it, actually there are several papers where people actually picked it up and they find the practical value in it. And there is quite a bit, because with K connectivity, so if you look at K block, you can have a K-connected graph that is not very cohesive because you can have a huge number of vertices in the graph. It's just like K-core, it's not very cohesive, right? So, but with S-bundle, removing all but S vertices to disconnect it, so it makes it a lot more cohesive. And moreover, it has some other structural properties that we'll discuss later that make it a good candidate for applying some standard type of exact combinatorial algorithms for detecting this structure. This was one concept that was not on the list yet, but that comes out of this systematic framework. In general, you can come up with a lot of useless definitions also based on this framework, right? So sometimes it could be like of pure mathematical interest, right? So, but in this case, this is one of the structures that actually has some interesting practical meaning, I would say. Let's look at the second type of modifications to elementary clique defining properties that we can use in order to define clique relaxation. So, and it was ensuring a fixed size clique property, right? For a fixed cardinality clique, let's say if I have a clique on K plus 1 vertices, I can define that a subset of K plus 1 vertices is a clique if and only if the degree of every vertex is at least K, right? So now, if I drop the part where I say of cardinality K plus 1, then I obtain the definition of a K-core, right? So this is the degree-based relaxation based on ensuring a fixed size clique property. So we get this definition. If we apply the same considerations for connectivity, we obtain the K block, right? So again, a subset of K plus 1 vertices is a clique if and only if it is K connected. So, and you obtain, again, we drop the cardinality part from the definition, so we obtain the definition of the K block, right? Okay, to summarize what we have so far in this taxonomy, so we have these clique relaxations. There are two types of rules that we are applying, right? So we already reproduced a good chunk of the definitions that we listed on that jungle slide, but not all of them yet. So let's see what remains. Quasi-clique is something that you can think of as a relative version of S-defective clique. So in S-defective clique, you have the number of missing edges that you allow in absolute terms, right? So S, and here you allow missing edges, but in relative terms. Relative to the overall maximum possible density, you need to require that at least a fraction of gamma of all edges is included in your subgroup, right? So this is what we call the relative clique relaxation. So where we use these parameters that express a fraction of something essentially as a part of the definition. So gamma quasi-clique is a relative clique relaxation. So we call a clique relaxation relative if its definition uses a parameter representing a fraction of quantity that depends on cardinality of the corresponding induced subgraph. Otherwise, if the definition does not involve such relative parameters, we call the clique relaxation absolute. So all the stuff we considered so far was absolute. Gamma quasi-clique is relative, right? So, but now if you think about relative, we have the quasi-clique so far, but now you can easily define the relative relaxations for other elementary clique defining properties, right? For example, what would be a relative club, let's say? Let's call it gamma club. So you could say that the diameter of the induced subgraph, let's say, is no more than 0.3 times the cardinality of the set or something like this, right? So look at the largest possible diameter that you could have. And the largest possible diameter is going to be given by cardinality -1, right? And require that it's no more than a certain percentage of the largest possible. I think in this case, making it relative of the size, just, yeah, that would be your definition, right? Now, these are some of the structures that nobody really studied. So these are some of the opportunities for the projects, So if you think about this framework, it opens up many opportunities. So, and again, you could define like essentially an exponential number of different structures here. So the question is, which ones are most interesting, right? So there is a mathematical definition. So mathematically, all of them are of interest. But we are engineers, so we want to only focus on the ones that are practically relevant, really, right? These relative relaxations, they typically make sense. So if the absolute version makes sense, then typically the relative relaxation makes sense as well, makes things a little more flexible, and in many cases it actually makes more sense to consider the relative versions, right? There are some papers on these relative relaxations that started popping up, but it's not as common yet as the absolute ones. Remember, we talked about the difference between S-cliques and S-clubs. We said that the S-clique definition appears to be weaker because it uses the vertices from outside to determine the membership in the group, right? That's something that leads to another type of categorization in this taxonomic framework. We will distinguish between the weak relaxations and standard relaxations. For the standard relaxations, we are focusing on the induced subgraph. So these are the stronger ones, and these are the ones that better represent the cohesiveness of a group, right? Here we'll use the concept of this pi set to make the definition easy to state formally. So we'll say that a set of vertices satisfying the graph property pi will be referred to as a pi set, right? So let's say if my property pi is clique, let's say. Then we could say the clique set, is the same thing as a clique, really. It's just a formality that allows us to use it generally instead of individually for each relaxation. So just let's call whatever property we are considering as pi capital, right? So then the subset of vertices that we have in this definition, we'll just call it pi set instead of saying S defective clique, S plex, and blah, blah, blah. Now we'll call a clique relaxation described by graph property pi standard if a pi set S in G is also a pi set in the induced subgraph G of S. So essentially this property is defined for the induced subgraph, right? So defining it for this set in the original graph and for this set in the induced subgraph is the same thing, all right? So in other words, the property is defined in the induced subgraph. Otherwise, we say that the clique relaxation is weak. Weak because we are using outsiders to deal with the issues within the group, right? So that's weak, right? Now we have another block here in this description of the taxonomy, right? So we have absolute relative, standard versus weak. Weak relaxations are not very common. Where would S-clique be more applicable than S-club? Can you think of any situation of this sort? Generally, I would say S-club is typically a more reasonable definition of a structure based on distance, right? So clique relaxation based on distance. But sometimes actually in many graphs, in many practical applications, S-clique is pretty much the same thing, right? So you can artificially construct examples where S-clique is not an S-club, but for the most part, let's say if I told you that finding the maximum S-clique is easier than finding a maximum S-club, then maybe you could try, let's say you really want to solve the maximum S-club problem, right? But if you cannot, and you could solve maximum S-clique instead quicker, and then if you were lucky and the solution that you found is an S-club, then great, right? So you found the optimal solution for the maximum S-club as well. So you could think of S-clique as a very good relaxation of S-club that generally may be a little easier to solve than S-club. All right? So that's For the most part, that's the role of these weak relaxations, and then they may be practically reasonable, slightly less reasonable than the standard counterparts, but still they make sense, right? If you use outsiders, in some cases you can think of it as an advantage. Introducing the diversity, don't disregard the weak relaxations. They have strengths. The weak relaxations typically involve distance explicitly or implicitly. Typically they arise when you can define your structure in terms of paths that may pass through vertices from outside. And then that could be implicit or explicit. S-clique is one example. Then you could define, let's say, weak K-block. And this has to do with an equivalent characterization of K-connectivity. Graph is K-connected if and only if there are at least K vertex disjoint paths between any pair of vertices in the graph. So you can define the concept of connectivity through the paths, right? This is a case of this implicit use of paths, right? So then you could define now explicitly, you can define a weak K-block based on this characterization through paths as a subset of vertices such that any two of them have at least K vertex independent paths between them, not in the induced subgraph as implied by K-block, but in the original graph. So these paths can use vertices from outside. And then last block that we're going to add to this taxonomy is structural and statistical clique relaxations. So all the relaxations that we discussed so far can be thought of as structural clique relaxations. You could also define statistical clique relaxations if you wanted to have a certain property, say on average, instead of requiring it to be satisfied for every single vertex. And remember, when you were talking about the small world networks, the average distance between any two vertices is short, right? So you could define a small world network. And in fact, I think there is a recent paper by some of my colleagues, Baginski and Veremyov, so where they actually look at these small world networks where it's a statistical relaxation, which requires that an average distance between any pair of vertices in the subset is no more than a certain value. And in this case, it could be, that value could be integer, fractional, and it could be expressed even in terms of a fraction of the total number of vertices, which would make it a relative statistical relaxation. There is a paper from 2005 that provides an example of a statistically dense group where they actually kind of criticize this as a definition of a cluster. They looked at this densest subgraph, which is a subset of vertices that maximizes the average degree of a vertex in the corresponding induced subgraph. And here they state that in general, statistically dense groups reveal only few insights into the group structure, which is at least partially true. So it's not as structured as structural relaxation. So that's why we call them structural. So you may have some areas that are very dense, some that are not so dense, and so on, right? So there is more diversity here, I would say, in terms of cohesiveness within the group. Let's say we could define the following statistical clique relaxation. So average K-core, a set of vertices inducing a subgraph with an average degree of a vertex greater than or equal to K, right? Average degree instead of all the degrees. So average S-club, a set of vertices inducing a subgraph with an average pairwise distance between vertices which is less than or equal to S. We can actually show that the quasi-clique can be thought of as a statistical clique relaxation based on degree. The definition of a gamma quasi-clique is what? So the number of edges is greater than or equal to gamma times the maximum possible number of edges, right? So now, if you look at the average degree of a vertex, how is it defined? So the average degree of the vertex in the induced subgraph is the sum of all the degrees divided by the number of vertices, right? So, but when you sum up all the degrees, what does it sum up to? So every edge contributes 2 to this sum. The sum of all the degrees is going to be what? 2 times the number of edges, right? So obtain 2 times the number of edges divided by S. I replace here the number of edges with the average degree multiplied by S and divided by 2, then this inequality becomes the average degree has to be greater than or equal to gamma multiplied by the number of vertices minus 1, which tells you what? Essentially, your average degree has to be at least fraction gamma of the maximum possible degree. So this is your statistical relative clique relaxation. Now, with statistical clique relaxations, instead of averages, you could actually focus on quantiles, essentially, like something that corresponds to quantiles in statistics or in probability. I could say that, instead of just averaging over the whole network or over the whole group, I could say that I'll call it, say, risk-averse statistical S-club. If, let's say, if I look at the worst 10% of pairwise distances in the graph, right? So I'm not looking at the average, but I want to be risk-averse, so I'm going to take, say, a small percentage of the worst distances, of the longest distances, and I want to restrict that to be no more than a certain value, let's say, right? So I know for sure that even the worst 10% of distances will be no more than 5, let's say, right? And I could add it on top of some other requirements, and we'll obtain a risk-averse version of my clique relaxation. Now we have this complete pretty much, all right? So even though there are many other different aspects, so we have this framework, and then we'll see that there are many things that we can do based on this taxonomy, all right? So it's very helpful in defining some interesting research directions, and essentially looking at things in a systematic fashion always helps to better understand whatever you are studying.